Hey, what's up guys? We're going to do a quick video over objects in free fall. This video is going to be featuring me, Mr. Jans, Mr. Schaefer, and then my made up girlfriend. Definitely made up. All right, let's get into it. So here is our scenario. As you can see, I'm an incredible artist. I know, I don't need you to tell me. All right. What is happening here is that Mr. Schaefer has whisked away my girlfriend, and he is on a nice little romantic evening out on the river with me and my girlfriend. You can see that they're sitting on this boat here, eating dinner, and I'm up here on this bridge to nowhere, and I am devastated. I'm just so sad that Mr. Schaefer has run away with my girlfriend, and I am contemplating what to do. All right, and I just want to absolutely destroy their evening. And so what I decide is that I'm going to drop a bowling ball and have it land, no, not on Mr. Schaefer's head. I'm just going to have it land on their dinner table and absolutely ruin their evening. All right, so there are basically three different things that I think that I can do here, and I need to decide which one is going to be better. The first scenario is to just drop the bowling ball. All right. Drop the bowling ball with an initial velocity of 0, okay? The second scenario that I'm thinking is, all right, maybe that's not going to give me the highest velocity that it'll hit the dinner table at. Maybe I need to throw this ball up into the air. So throw bowling ball upwards. And let's say we give it an initial velocity of positive 8 meters per second. And the second scenario would be to throw the bowling ball downwards. And let's say that we throw the bowling ball downwards at the same rate. Let's say V initial is equal to negative 8 meters per second. We're just changing the direction, all right? Three different scenarios. I want you to think to yourself right now, all right, which one of these scenarios is going to give me the highest velocity when it hits this table, all right? So let's go ahead and figure this out. Scenario number one. Scenario number one, we are looking for what is the V final. So let's write out what we know. Now, looking at this right here, let's say that the distance between me and Mr. Schaefer is, let's go with 85 meters. All right, so that's 85 meters. And let's say that the acceleration is equal to negative 9.81 meters per second squared. And let's call our reference point the table. All right, so table is going to be our reference point. So let's think about this. I'm 85 meters above Mr. Schaefer. My ball has an acceleration of negative 9.81, and my initial velocity is 0. So V initial is equal to 0. V final, we don't know. Acceleration is equal to negative 9.8 meters per second squared. The change in Y, and the reason I'm calling it the change in Y is because if you can imagine a scale, I've got the Y world and the X world, all right? Up will be the positive Y direction, and to the right will be the positive X direction. So if I'm going down, like this ball is going down, my change in Y is going to be negative 85 meters. All right? So, and I also don't know time. The two equations we can use, we've got V final equals acceleration times time plus V initial. And we've also got this one, delta X is equal to 1/2 AT squared plus V initial times time. And one thing, sometimes you'll see me write this, sometimes you'll see me write this. Those are the same thing. They represent V initial. Now what's annoying is physics, there's just so many ways to notate things. I'm going to write both just so you get used to seeing both. All right. First thing we need to do here is we need to solve for time. Time is the thing that will help us find that V final because time exists in both of these equations. The place where I'm going to solve for time is in this equation right here. So first thing I want to do is I want to take that equation and I want to rearrange it to solve for time. All right. I want to solve for time algebraically. So I got delta X equals 1/2 AT squared plus v initial times time. First thing you want to think to yourself is there anything I can get rid of? Well, yes, there is something I can get rid of because my initial velocity is 0. So that term on the end is going to disappear. So that leaves me with delta x equals 1/2 at squared. Now I'm going to do some algebra to get t by itself. So that becomes 2 delta x over acceleration is equal to t squared. I take the square root of that, and I get that time is equal to the square root of 2 times delta x divided by acceleration. And now we just plug in our numbers. So this is 2 times negative 85 meters divided by negative 9.81 meters per second squared. And I take the square root of that, equals my time. And we get 2 times 85 divided by 9.81. Take the square root. Get, oh, hold up. My bad. I'm having trouble calculating here. 2 times 85 divided by 9.81. Take the square root. All right, 4.16 seconds. That is equal to my time. All right, let's see if I can do this better this time. I want to select all of that. I want to group this together. And then I'm going to just resize and put this in the corner. All right, so I solved for time. Now we are going to solve for final velocity. Solve for v final. All right, and I can use the first equation to do that. I've got v final is equal to acceleration times time plus v initial. And I know that v initial is 0, so that's going to go away, which leaves me v final is equal to acceleration, negative 9.8 meters per second squared, times time, which was 4.16 seconds. Now, when you do this calculation, use the full number for time that you got when you calculated it. So make sure you save that on your calculator, have that whole number there so that you don't round, all right? Now, when we do this, we end up getting that the final velocity is negative 40.84 meters per second. So scenario 1 gives me an impact velocity of negative 40.84 meters per second. That's pretty good. Let's check out scenario 2, though. All right, scenario 2, the only thing that's changing here is that instead of having an initial velocity of 0, we have an initial velocity upwards of positive 8 meters per second. So if you can imagine what's happening here, what I'm going to be doing is I'm going to be taking the bowling ball right here. I'm going to be throwing it up into the air. Then it's going to come back down all the way to the table. All right. So v initial is equal to positive 8 meters per second. It's positive 8 because we defined the positive y direction as up. V final, we don't know. Acceleration, negative 9.8 meters per second squared. Delta y is negative 85 meters. And time we don't know again because this time is going to be different. And you have to think to yourself, is this time going to be greater or smaller than the time we got in the first value? And we're going to expect that time to be larger because our ball is going up and down. So conceptually, we just need to be thinking that it's going to be larger. Again, we're going to start by solving for time. But when we do it this time, it's going to be slightly different. All right, solve for time. So we're going to use that equation again. We got delta x equals 1/2 at squared plus v initial times time. This time, though, my v initial is not 0, so that's not going to go away. All right, so let's just plug in and see what happens. We get negative 85 is equal to 1/2 times negative 9.8 t squared plus 8 times t. So we cannot factor this easily. So what I'm going to do is I'm going to bring the 85 over to the other side, and I get 0 is equal to negative 4.9 t squared plus 8t plus 85. Now, as we've learned in math, we're going to take the quadratic formula and solve for t. So t is going to be equal to negative b, which is negative 8. And actually, I'm going to write these out so you can see them. A is equal to negative 4.9, B is equal to 8, C is equal to 85. So T is equal to negative B, negative 8, plus or minus the square root of B squared minus 4 times A times C divided by 2 times A. Now I'm going to get two different values for time here. And what I want to keep in mind with these two values for time is that I am looking for the value for time that is positive. All right? So I'm going to get an expression that says negative 8 plus or minus 41.59 divided by negative 9.8. So two values I can get here are going to be, if I take the plus version of that, that's going to be divided by, if I add that, it's going to be negative 3.4 seconds, or one sec, negative 8 minus divided by negative 9.8, or 5.0 seconds. So those are my two options here. All right. Now let's look at what we had expected. So negative time not going to work, so we're going to cancel that out. 5.0 seconds is greater than what we got in the previous problem, so that makes sense. So 5.06 seconds sounds pretty good for my time. All right, but we're not done yet. So let's see if I can do this quicker this time. There's that group. Put this over here. Now we can solve for the final velocity. So same process. Solve for v final. We get v final equals acceleration times time plus v initial. So v final is equal to negative 9.8 times time, 5.06, plus my initial velocity of 8. So this becomes negative 9.8 times your time you just calculated. Again, don't round. Plus 8. I get negative 41.59 meters per second. And if you look at that, negative 41.59 is greater than negative 40.84. I know that they're both negative, but what I mean by greater is that the magnitude, and remember the magnitude is simply the number. The magnitude for 41.59 is greater than 40.84, and they are acting in the same direction. All right? Now we're going to go to scenario number 3. In scenario number 3, what is changing here is that now instead of having our initial velocity directed upwards, our initial velocity is directed straight downwards. So I'm throwing this thing straight down at Mr. Schaefer because I'm just so upset at him, but I'm throwing it with the same magnitude as I did before, but just in opposite direction. All right? So going through this calculation, v initial is now negative 8 meters per second. We don't know v final. Acceleration is negative 9.8 meters per second squared. Delta y is negative 85. Time, we do not know. All right. Now in this case, it's going to be the exact same process as what we did before. All right. So looking at the way we solved for this originally, we had all of this going on, except what was happening originally was we had a positive initial velocity. So there's our initial velocity, there it is, and there it is. I want that initial velocity now to be negative. So all of these are going to need to change. All right. So I'm going to go through and adjust those. So that's no longer positive, that's no longer positive. And then we're going to get a different number at the end. All right. So let's make our revisions. This is now negative 8, minus 8, minus 8. This is a negative negative 8. So that's a positive 8 at the beginning of the quadratic formula. This becomes negative 8 squared. And we're set. So now I've got 8 plus or minus the square root of that whole thing. So we get, let's see here, 8 plus that divided by 9.8. All right. And then we get 8 minus that divided by 9.8. And we get a time. Why am I not getting this right here? I'm sorry, guys. Give me 1 sec. 8 minus 41.59 divided by negative 9.8. Okay, there we go. And we get a time of 3.43 seconds. I know it's going to frustrate some of you. I'm going to rewrite that in blue. 3.43 seconds. This time should make sense because my original time was 4.16. That was when I dropped it with an initial velocity of 0. Now I'm throwing it down, so I would expect to reach the ground faster than I did before. All right? So we got our time. Now, let's go ahead and solve for our final velocity. All right? So I'm going to put this up in the corner. Final velocity we solve for just as we had before. I'm going to plug that time in. Solve for VF. I get V final is equal to acceleration times time plus V initial. V final is equal to negative 9.8 times 3.43 plus negative 8. So I get V final is equal to negative 9.8 plus negative 8 is equal to the exact number that I got in the previous problem, negative 41.59 meters per second. So the moral of this story is that regardless, so my initial velocity was the same in both scenarios, for scenario 2 and scenario 3, except for the direction. And so what this tells me is that if the magnitude of those initial velocities is the same, the direction doesn't matter because I'm going to have the same final velocity. All right? Let's go through and do the position versus time graphs for each of these real quick. So, scenario number 1. I'm moving in the negative direction and I'm speeding up. So I've got a negative velocity, a negative acceleration. I'm speeding up. Let's look at that position time graph. So, position versus time, I start here and then I speed up in the negative direction. Boom. Now, scenario number 2 is a little bit different. All right. Initially, I have and this over here was a initial velocity of 0. In scenario 2, I have initial velocity of positive 8. So I move up and then I move in the negative direction. So I slow down and speed up. So what we have here is initially I am moving in the positive direction and slowing down. Then I reach the top of my motion and I move in the negative direction and speed up. In scenario number 3, spelled that completely wrong. We have velocity initial of negative 8. We have a negative acceleration, and we speed up the entire time. So what we end up getting there is an initial velocity down, and then we speed up. Things that should be the same between these graphs. The slope at the end of these graphs should be the same. This is because we calculated that the final velocity was 0. So this represents the final velocity. Other things to notice. The initial velocity here is 0 because the slope is 0 at the beginning. This point right here is a turning point. That's where the object hit the top of its motion and then it turned around and started heading in the other direction. So let's look at what these velocity time graphs are going to look like. In scenario 1, God, I spelled scenario wrong again. Unbelievable. Unbelievable. This is why I'm not an English teacher. Scenario 1. So we had a negative slope that was increasing. So my velocity is in the negative velocity and I'm speeding up. So looking at my velocity time graph, negative velocity tells me I'm in this quadrant right here. And what I'm going to be doing in that quadrant is I'm going to be moving further away from the x-axis. Boom, moving away further from the x-axis. In scenario number 2, this one's different. Scenario number 2, I have a positive initial velocity. And for the first part of my motion, I have an initial velocity in the positive direction, and I slow down. The reason for that is because I have a negative acceleration. Then I have a negative velocity, and I speed up because I still have a negative acceleration. So I need to have two sections of motion here. So my two sections of motion, initially, positive velocity and slowing down. Positive velocity tells me I'm in the positive quadrant and I'm moving towards 0. Then I have a negative velocity and speeding up, so I'm moving away from the x-axis, just like that. Finally, scenario number 3. Maybe. Okay. Scenario 3. I swear, if I spell scenario wrong, one more time. Scenario 3. So here, we've got a negative v initial. We are speeding up, and we have a negative acceleration. So the only difference between scenario 3 and scenario 1 is that I'm starting at a more negative location. You can see that my initial velocity is negative, whereas here my initial velocity was positive. All right? Now, the acceleration versus time graph for all of these, I'm only going to draw one, is this right here. Because if you look at these graphs, the slope of each of these lines is the same. It's negative and it's constant. It's negative and constant because we made the assumption in each scenario that our acceleration was negative 9.81 and constant the entire time. All right, guys, I hope you found this video helpful. We'll be doing more problems like this. Let me know if you got any questions. Talk to you guys later.